Hopefully we're live now. Looks like it. And let me hit the pause over here. So again, page 89. Oh, whoops. All right. So that's, I guess, a quick review. Page 83 was the definitions page. So if you need that, just keep aware that's where that is. And I think I said 89, right? All right. So let's do a bunch of problems that have 1 as the only number in them. That's this page. So you have a space probe. It's essentially a solid disk. It's got a retractable antenna. It's rotating about the dotted line shown in the figure at 2.80 RPMs, revolutions per minute. The probe then extends its antenna to signal Earth. So maybe you could say this is a bad design, but whatever. It makes for a good practice problem. That's all we care about here. The probe then extends when it's fully extended, the edge of the antenna is essentially at the edge of the disk. The mass M of the antenna is equal to this. All right, what's your gut tell you here? Should we do an energy problem, angular momentum problem? What do you think and why? Take a guess.
RPM stands for revolutions per minutes per second, right?
Revolutions per minute. RPMs, meaning revolutions per minute. I don't know why, but I guess I should have left the S off. I can't help it. Like, that's probably bad form. You probably just caught me doing something that's bad form. 2.8 revolutions per minute is already plural, but sometimes people just say how many RPMs was the thing going, and maybe that's just the small town hick in me or something. I don't know. Is that good, Gonzalo?
Yeah.
Revolutions per minute.
In that case, I think it's gonna be energy.
Okay, and why do you think energy?
Because I'm thinking like speed and velocity, and those things are usually the ones we use for energy.
Okay. So I'm going to offer a counter argument. I know this is cheating, but this is chapter 11. It's probably angular momentum, right? So
Yeah.
your thought process was a good idea, but it turns out it's totally wrong. We should not use energy for this. In fact, look at part F. Sorry. Do you see how the energy is? We see that it's going to change, or at least it looks like that. That's a sign we probably can't do E initial equals E final for this problem. Now, it turns out we'll discuss this more later, there might be a way to do it, but it turns out it's not obvious and it's not easy. It's actually very difficult. So that was a good guess. And that's the problem, is it looks exactly like an energy problem. Why is it okay to do it as an angular momentum problem?
Because it's spinning.
What else? What has to be true if we want to do an angular momentum problem? Do you remember?
I can double check. For angular momentum, no external forces.
Torque.
Or yeah, torque.
What page are you on? Or is that just your notes?
Oh, just my notes.
Yeah. Oh, so if it helps, let me remind you of something right here. Sorry. It's somewhere here. The big three conservation laws on page 93. Page 93. Yeah, there it is. If you want to use conservation of energy, we need there to be no external or non-conservative work. If we want to use angular momentum, L initial, L equals L final, we need no external torque. If we want to do conservation of momentum, we need this to be true. So let's go back to our problem. Somewhere here. This one. So you're in deep space, aren't you? Yeah, so we're assuming you're some space probe. There we go. It's a space probe. So it's somewhere deep in space, rotating slowly at this fixed rate, right? And so if it's rotating at that fixed rate, that's kind of the clue that, well, if it's in deep space, the sum of, there's no external anything. Sum of external torques is equal to 0. And that is why it's okay to use angular momentum. Now, it's not obvious. There's no external work either, but there is non-conservative work. And that's the issue, Gonzalo. There's non-conservative work when you extend this out. And I'll explain more about that in a minute when we get down here. I address that down here. Gonzalo, is that okay?
Yeah, that's just not really super obvious to me.
It isn't. And unfortunately, this is why this chapter is so hard, because we're at the point where you have enough tools, they all start to kind of look the same. You have to learn what aspect of this problem gives it away as an angular momentum problem, right? There's no way around that except experience and lots of practice. So I'm going to help you with that later, okay? Let me put it to you this way. Doesn't this kind of look like a figure skater putting her or his arms out? It's rotating and then the arm kind of sticks out. Can you see that a little bit, maybe?
Yeah, the extended antenna thing.
Yeah, and that's what makes me think of angular momentum. If I could think of a problem as a figure skater, arms in, arms out, that's the clue that makes me think it's an object changing shape while rotating, angular momentum. Got it? That's kind of the practical. Now, all right. So the moment of inertia, I think you can get that. Where's the center of mass after the antenna is extended?
It stays the same?
No. Let me ask you this. Where is the center of mass in the first problem?
In the center?
It's right there, right?
Yeah.
Well, here's some mass. There's some mass. Where's the center of mass now?
It shifted to the right?
Yeah, and they both have the same mass, so is it closer to the disk's center or closer to the rod's center?
Discs?
The same. They have equal mass. If they're both the same mass, it's right there. Does that make sense? It doesn't matter how that mass is distributed for the center of mass. This point object has its center of mass right here, or sorry, that object can be treated as a point mass right there. This object can be treated as a point mass right there for center of mass calculations, and that's what gives rise to this new center of mass. Got it? All right, so that's that one. What do you think is going to happen? Is the final moment of inertia going to be bigger, smaller, or the same? What's your gut?
I think it'll be bigger when it's extended
Why? Why? What is your reasoning?
because the same reason that figure skaters bring it in to lower the moment of inertia.
Meaning, I'm not saying no. I'm just trying to understand
Oh,
more.
well, meaning like it's gonna rotate slower.
Okay. Okay. Yes. The phrase I'm looking for is which of these objects has the mass closer to its axis of rotation, which is kind of what you were alluding to, but I want to use those words. So,
Oh, I
Right.
get you.
so it has the same amount of mass. Which one has the mass far from the axis of rotation? The upper picture or the lower picture?
I think the lower one.
Yeah, absolutely. Where is the axis of rotation in the lower picture?
Where
The
the
center.
The center of mass. So look, here, a lot of the mass is really close to the center. Here, a lot of the mass is far from the center. Now, the axis of rotation used to be right here. It's now moved to here. And that's the issue that this problem is a little bit weird, right? So this is a terrible design for a satellite. When you want to send a message to Earth, you have to change the axis of rotation of the satellite, which changes the rate at which it rotates, and it could be problematic. So it's a terrible design, right? It would be better if the axis extended out this way along the axis, because that wouldn't change anything. But that's not how this one was built, so who cares? All right. So how do I get this new rotation rate? What would you do? Just kind of walk me through your thought process, how you might attack this problem. We're supposed to figure out the new rotation rate in RPMs. What do you think?
Use parallel access.
Okay. That would be for getting the moment of inertia, right? Because the parallel axis theorem helps you get the moment of inertia. So, okay, yes, you would use the parallel axis theorem and we would get that.
Would it have to be anything with the period for the frequency?
Okay, what about that frequency?
Frequency is the revolutions over seconds.
Okay. Where do I plug that into? You need an equation. What equation do you reach for?
I was thinking the angular velocity.
Okay, now we know that this is omega. So we know omega is that. What other equation can we use omega in? What equation can we shove this number into?
V10.
That would give you the velocity of a particle on the edge, but that's not what we want, right? This has some initial rotation rate, right? And we're asked for the final rotation rate.
This is just a guess, but what about angular frequency?
Oh, angular frequency is omega.
Oh,
Yep.
Would it be the rotating object changes shape? So
That's what I'm talking about. Tell me the equation.
it's going to be the initial inertia times the omega initial equals inertia final and omega final.
So that's what I was trying to set people up for. This was actually an old test question. It's in the book because a lot of people had trouble with it. So I was trying to foreshadow that in part A, that at some point you've got to write down angular momentum. So I told you we need to use angular momentum, and then I'm setting you up, right? Angular momentum is this. So you should be thinking this. Rotating object changes shape, write that down. And you're still new to this. So that's why we're going over it now. So don't feel bad if you didn't catch that right away, but that's what I want you to instantly think when you see this problem. Figure skater or rotating object changing shape, write down this equation. So I need this because that helps me figure out that, and then that helps me solve for omega final. So let's take a look in the solutions and see what happens here. This is 1111. Okay. So if you care about that energy statement, here it is. All right, blah, 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 blah. Okay, so here's the initial moment of inertia. The trick here is the length of the rod is, how long is the rod?
$2R.
2R. So you got to shove in 2R, and that's how I get this number. And then we discuss this. That's just doing a center of mass calculation. Afterwards, if the disk is now at the edge, this is what Denna was saying, parallel axis theorem. And then we just shove this crap in and we get this weird result. And I did look it up. It should be RPM, not RPMs. So I'm a bad person. I can't help it. That's the I don't know, the hick in me or something. I don't know. Now here's change in energy. I think you could follow through that. So it actually loses about 70% of its energy. That's a very inefficient satellite, right? Every time you have to send a signal, you lose 70% of your rotational energy. Now, maybe you would want that. Maybe you don't want it to rotate, so then you could just keep moving the antenna in and out, using up rotational energy. But that seems like there's a smarter way. By the way, notice this negative 12/17. You don't say it loses negative 70%. We say it loses 70%. So the negative sign turns into the word loses. All right. Let's go back to that question here and look at it again. Okay, so let's try and go through these concept questions down at the bottom again. How does the period change? Let me ask you, is this thing going to speed up or slow down?
Should slow down.
Slow down. So what happens to the period of rotation?
Should be decreases then.
Increases, takes more time to go around. Omega goes down, but remember that omega is equal to 2 pi over the period. Is that what you needed, Jess?
Yeah, I just got mixed up. Yeah.
Yep. So this is, and you could see why I put this on there. It's that extra step of remembering if omega goes down, the period goes up. Takes longer. So just watch out for that. With these kinds of concept questions, it can help to kind of think through a numerical example. Say if it slows down, it takes more time to rotate, period increases. How does the probe's angular momentum change? Go ahead and take a guess, somebody. It's okay to be wrong.
So angular momentum is L, right? And that's moment of inertia times omega.
Right.
So and when it extends, that means you have more moment of inertia. So that should mean it decreases.
Nope.
Oh,
Remember, that's how we did the calculation. The increase in moment of inertia is directly offset By the decrease in rotation rate. That was, oh wait, I wrote on the wrong one. Crap. I read the wrong line. Sorry. Give me a sec. This one stays the same. There we go. That's angular momentum. Isn't that how we started this problem? Just saying L initial equals L final. Make sense?
Yeah.
Yeah. So that was, now, how about the rotational kinetic energy, Gonzalo?
Okay, that should decrease.
That will decrease. So here's the trick, right? The rotational kinetic energy is 1/2 I omega squared. Whereas in the angular momentum, it's I omega. So we know that if these two stay the same, if I goes up, then omega goes down. But then when you look here, if I goes up, omega goes down squared, twice as much. And so this one will dominate the energy term. While not always true, it's hard for me to think of a case where if you slow down, you actually get more energy. There actually is, there's a weird case in the atmosphere with drag, but let's not go there. All right. Next. How does the probe's translational kinetic energy? So I want to be clear. The previous one was talking about rotational kinetic energy. Now I want to talk about translational. Go with your gut. Again, it's okay to be wrong. We're going to talk about it. What do you think for translational kinetic energy, somebody?
Stays the same.
Yes, it will stay the same. Why is that, in your opinion?
I think because it's in space, so there's no external forces.
Okay, if there's no external forces, I like that. There's no external forces. What is conserved if there's no external forces? Do you remember? Is it angular momentum, energy, or linear momentum? Do you remember?
Momentum isn't conserved, but
It should be
angular.
linear momentum.
Momentum is conserved. So when I say momentum, linear momentum, I'm using those terms. So sum of torques equals 0 is what allowed us to use angular momentum. So let me write that over here. If we have sum of torques equals 0, if that is equal to 0, that is what tells us we can use the angular momentum. If sum of forces equals 0, then we could use this. Now, you may not be familiar with this, but if the mass isn't changing, if the mass is constant, hopefully you could see that the velocity then remains unchanged. If the mass is remains constant. Do you agree with that? The mass will cancel out. I think of it another way. This is a little bit strange, but I want to show you this one. You probably, what's the equation for kinetic energy that's translational? 1/2
MV squared?
mv squared. Now, I'm going to write this another way so you could see it even easier. P squared over 2m. Now, I know this seems strange, but just kind of verify that. The p squared would give me too many m's on top, so I divide it out right there. I still have the half. But that allows you to see that if you have no external force, that directly leads to your translational kinetic energy does not change. Got it? So that is good. Okay, and then I think we already talked about bullet point K. It's at the center of mass. Okay. All right. Let me do this really quick. I just want to stress this one last time. Let's see if this whiteboard falls over. This is kind of the thing that we saw just a minute ago. If you have one of these rotating objects that changes shape, this thing equals that thing. If this doubles, so if this is twice as big, omega final has to be twice as small, or vice versa. And again, the issue that I wanted to stress here is that shows us that the rotational energy does change, right? This gets cut in half. This would be quadrupled. So you actually double the energy. So if your moment of inertia cuts in half, your rotation rate doubles, and then you have 1/2 here times 4, you actually get a doubling of the rotational energy as well. Questions on that? All right. Still live to fight another day. All right. You ready for another one? Or any questions about that? Let's try another one, all right? So we're going to try and do 3 problems today, and then the third one, I might give you a breakout room to let you zone out. But before that, let's get nasty. 11-point nasty. Whoops. Before you think, oh man, Jorsted's so mean, this is actually a fairly standard physics problem, believe it or not. That doesn't mean it's easy. It's I would say a difficult problem. Actually, let me say very difficult, but it is a standard problem. We're doing this one because you really, really, really have to learn and know what applies in what situations. So let's read this. A bullet of unknown mass travels with speed v just before impact with a wooden plate. The wooden plate has mass m and side length s. Got it. After impact, the bullet embeds in the top left corner. Let's see. There's a small wedge fixed to there. Oh, so that's what that little black thing is in the corner there. This right here is basically something that acts as a pivot point, right? When the bullet hits, it causes the bullet, oh, this should say block, shouldn't it? Causes the block to tip over. Let me write that down. I got to fix that. Okay, got that written down. Sorry. Okay, so that's supposed to say plate right there. Causes the plate to tip over. Okay, so let's try and figure this out. Any ideas how we might attack this? Anyone? What's the first thing you might try? It's okay if it's wrong. What's the first thing you might try on old 11-point nasty here?
1 or 2 objects rotating with collision.
Okay, so what would you write down for that? You said 2 objects rotate with collision. What does that make you think to do? What should you write down then?
Got to find inertia, and then you got to find omega.
Okay. Yep. So I think you're probably saying this, right? I1 omega
1 initial.
Yes, right. That
Plus-
kind of thing.
Yeah.
Okay, I'll write that down. What do we usually do when we have this equation written on the paper? What's something else we usually do? Starts with the letter D. Most physics problems, we do this.
We could probably draw a diagram.
Draw. Now, do you agree this has an initial and a final in it? Here's the initial. I'd better draw the final. Otherwise, I'm hopelessly lost, right? The bullet embeds. What's going to happen to it after that bullet hits the plate? What is the plate going to do?
Kind of want to move to the right, but because of the pivot, it's gonna rotate.
Rotate, not translate. The pivot keeps it from translating. That's the whole point of that chunk down there. It makes it tip instead of slip, right? It makes it rotate instead of translate. So there's going to be some rotation right here. What's true about this side of the equation? Is there any way I could simplify that?
The moment of inertia 1 and work 1. Would you say it goes to 0 because it's one object?
Okay, yeah, it goes to one object. So I was going to say, couldn't we group the two moments of inertia? Right?
The bullet inertia is still there for the second half?
Yeah, it is. It's probably small, to be honest. It's probably very small. So you could argue, is this negligible? Maybe. But if we're not sure, let's leave it in for right now, okay? Is that cool?
Yeah.
To be honest, I think the moment of inertia of the bullet is probably much smaller than the moment of inertia of the plate, because usually bullets are much smaller mass than the plates. However, it does have a large radius, so I'm not quite sure on that. Okay. But yeah, that would be a good first approximation, Alonzo, and that would probably get you close enough to get the job done in a real world application. Probably. I just don't want to go there yet. All right. Well, what about this term? Do you know any tricks that we could apply for this term? I guess I'm assuming 1 is the bullet, right? Because I said M1 is the bullet. So I'm going to label this. This is object 1. This is object 2. Do we know any shortcuts or tricks so that I don't have to do so much work for that first term? There was a shortcut. I think it was on page 83. I'll check if it was page 83 or not. What do we do when you have a point mass? Instead of I omega?
Our omega?
M V R perpendicular. Do you remember that? That's what I was trying to go for there. Sorry if that didn't make sense.
So are we treating the bullet as a point mass?
The bullet is effectively a point mass. Absolutely. Good. Do you think that's reasonable?
Yeah, because it's like it has a basically negligible mass.
And it's small compared to its distance from the pivot. Both of those factors. It's not so much the small mass as it is its small size relative to the distance from the pivot. You remember that problem where I said, when can we treat a sphere as a point mass? And it was something like anytime it's more than if this distance here we called x, if x is greater than about 6 to 7 of the sphere's radius, we could treat it as a point mass. Just looking at this picture, while we don't know this, this object looks much smaller, and in practice, we know bullets are very small compared to their distance away. So, Gonzalo, you good on that?
Yeah, that makes sense.
Yeah. See how hard this is? You're expected to estimate all the time and make these assumptions. As an engineer, one of the things you have to do all the time, you have to think about what assumptions you can use to get an answer that's close enough to correct that it's useful. That's a key issue with engineering, is thinking about your assumptions. When can I say this is legit? When can I not? And the only way you can know is practice. Hey, that's what Allen Iverson says. Are we talking about practice? All right. Next, what's omega 2 initial?
Zero?
Yeah, at least something was easy. All right. Woo! So that's going to help us figure this out. Now, I want to point out, let's remind ourselves, what do we not know in this problem? What is an unknown? Do you think we could figure out the moment of inertia I2, for example? Is that something we could, in theory, figure out?
Yes.
Yes, we're going to get that. How about M1? Do we know M1?
Yes. One, the bullet, or two bullet?
The bullet is 1.
No, we don't.
So that's an unknown. What about R perpendicular? Obviously, we know V. I see V right there. So V, we've got it. Do we know what R perpendicular is? What the heck is that? Do you remember? Or how did we go about finding this weird thing, R perpendicular?
R sine theta.
Okay, what was one of the first things I drew?
Your
Line of motion. And then that is R perpendicular. Do you agree?
Yes.
So what is the value of R perpendicular in this problem?
S.
S, and we know it. Ding, 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 ding. All right, so we're getting there. What about omega final? Do we know that?
No.
No. What about I1? Do I know that?
Yeah.
No, we don't know M1. M1 is a part of that. So it looks like we know it, but we don't, because M1 is the unknown that's on both sides of the equation. Ah! So, but pretty much we have two things we don't know here. If you wrote this out very carefully, there's two things that we don't know: omega and M1. And we're trying to figure out M1. What should we do? What do we need if we're going to solve this? We've got two unknowns. We've got one equation. What is required if we're going to solve this? Sorry, my question's probably bad. How many equations do you need if you have two unknowns?
Two.
Two. You probably heard your math teacher say 2 equations, 2 unknowns, solve it. Well, we only have 1 equation, 2 unknowns. We need another equation. Crap. So that means we got to keep working. What should I do? And I know you could look at the solutions, but let's try and struggle through this to kind of get a feeling for it, all right? And if you don't like the way I'm teaching it, I'm not offended if you just start working out of the solutions. I'm trying to kind of guide you on this one, all right?
Could you do L final equals M1 plus M2 VR?
No, I don't. I don't. We basically already used the angular momentum issue. So we could try and do angular momentum a different way. It's either going to be an invalid equation or it will reduce to the same thing that we've already written. And that might be what you were just saying. I think it'll end up working out to be the same thing that we're doing already. So that was a good idea, but we've already used angular momentum during the collision. There's nothing more we can get out of that. We have analyzed the crap out of this collision. What else is happening in this problem? After the bullet hits, what happens?
Should rotate, correct?
It should rotate. What are we trying to get this thing to do when you shoot it with the bullet?
Trying to get it to
Flip all the way around, or
Yeah. So what's something, let's talk about that. What's something we could maybe do with that?
oh, the arc of the bullet
Okay, what do you mean? think-
when it hits the plate, it makes an arc as it
Ah.
to the other side.
So this thing is going to go up and over and land on the other side. So what's something we usually do in every physics problem to help us visualize that kind of stuff?
Draw it out.
Draw. Where should I draw the plate with the bullet in it next?
Like a diamond.
Yes. Why a diamond though? Why not all the way over?
That's the highest it goes.
That's the highest it goes. So what should be the speed of this plate as it rotates if we're up here at the top? How fast is it rotating if we just barely get this thing to tip over? What's the rotation rate when you get to the top? If you're just barely able to get over, is it rotating quickly or slowly as it reaches the top of its motion?
slowly, so close to 0.
Yes. So if we set this omega equal to 0 when it's at the top, how could I compare stages 2 and 3? What should I do to compare these two stages? Should I use angular momentum? There's a bullet in there too, right? How do I compare stages 2 and 3? Is there a conservation law I could apply? Does it look like angular momentum is conserved? Initially, at the start of stage 2, does it have angular momentum? At the start of stage 2.
I would say it has a lot. So because it
Yeah. And
starts
then
moving,
what about in stage 3?
it has
When it's
nothing.
up at the So is angular momentum conserved?
No.
No. In the real world, yes, but that's because the planet slows down or speeds up. But we can't observe the planet's motion, and it's so small we don't notice it. So, yes, angular momentum technically is conserved if you include the entire planet Earth's angular momentum, but we can't do that practically. So, L initial is not equal to L final because there's no way for us to account for the Earth's rotation. Let me see what's in the chat there. Oh, sorry, Mark. All I could see is my screen right now. Sorry, I've got the screen up so that I make sure I don't screw up. So I don't see anybody nodding. My apologies right now. So basically, it's mute or it's either unmute or speak to me during chat. Sorry, with this thing up here. I just don't have enough space to keep all your faces up here. Sorry about that. So this is not going to work. Well, what about regular momentum? Is that going to work? What do you think? What about linear momentum? Would this be a good candidate to use linear momentum? Ah. What do you think? I say no. Technically, it is conserved if we could include the entire universe. However, again, the pivot point exerts a force on the plate. That's an external force that causes linear. So take a guess what we should do to compare 2 to 3.
Energy problem?
Very good. Very good, sir. All right. That is how we could handle this. Here's how I think of it. Collision between stages 1 and 2. Collisions, momentum. One object swinging around. It's basically a pendulum, upside down. This is called an inverted pendulum problem. A pendulum, usually we do energy. Piece of cake. Now, in this problem, usually the work goes to 0. Yeah, now you know why it's called 11-point nasty. It's in a lot of physics textbooks, though. All right. So what's one of the things you do in a energy problem? What are the types of energy involved here?
It's rotational. Rotational is one, correct?
Okay, we got RKE. So there's going to be a 1/2 I total. Omega squared initial. What other kinds of energy?
Translational?
No, it's not translating because the pivot keeps it from. Now you could argue, wait, isn't one? Yes, but we've already accounted for that. If you have a swinging pendulum, we're going to view that as pure rotation, no translation from an energy perspective. Does that make sense?
Yeah.
Why?
Yeah.
If it was rolling, if you hit something and it started rolling, that would be different. Oh, I should have done that for the final exam. Next year. That's a great idea. Thanks for that one. All right. So there's no translational because this is pure swinging motion, only rotation. What other kinds of energy? I'll wait for it. Gravitational. Where do we need to worry about the gravitational energy?
On the
What subscript do I usually put on this term other than just initial?
The bullet?
Center of mass. Well, okay, which, like Dennis said, accounts for the bullet. Now, let me ask you, if we have just the plate, the center of mass would be right there. Agreed?
Correct.
If you add a bullet to that, do you think the center of mass will shift much?
A tiny bit, but hardly any.
Yeah, and even less than the moment of inertia changes, because the moment of inertia had an r squared in it, right? So there's a reason that we might expect the moment of inertia to change, but yeah, okay, got it. All right. So what's something else we always do in a gravitational problem? Or sorry, in a center of mass problem where gravitational energy changes? What do we always draw?
The reference point?
Reference level. Why not just set it right at the center? It's going to be a little below there, right? And so this is the height we need to figure out. Height final about the center of mass. What do you think? That's the whole problem. Are you ready to take a look at the solutions? Or before we do, any questions? Let's take a look at it. So I spent a lot of time on this one for you, all right? So far, so good. There's our R perpendicular. There's our omega. Oh, shoot. What's the moment of inertia of that plate? That's one more piece that I think we should figure out. What's the moment of inertia of the plate? Just the plate. Forget about the bullet. Tell me the moment of inertia of the plate.
Maybe the 1/12 m.
What page are you looking at? So everybody knows.
Page
59.
59.
59. Everybody look at page 59. There's two plates. Which one is it? Alonzo, take your guess.
It's the 1/12 m and then parentheses b squared plus a squared.
Okay, b squared plus a squared. Now, what is a and b, and why did you choose this one over the other one?
The axle of rotation is going out of the
plane.
plane, but it just shifted.
Yeah, so if you look in the upper table, there's one of them where the axis runs in the plane, which is just 1/12 b squared. Remember that? Then there's another one where the axis is like this, where it's running perpendicular to the plane, which looks more like our example. So what is A and B for this particular plate?
B is S.
They're both S in this case.
Right.
All right. So do we know the moment of inertia of this plate then?
Yes.
That's not it though.
S squared.
When I do all this, don't I get just 1/6? Do you agree with that? But that's not the moment of the inertia of the plate in this problem. Why?
Because it's not in the center. Right?
Yeah, so that's the moment of inertia about the plate about its center of mass.
So we
I
use
need to do I parallel. Right?
This might be different because it's diagonally. It's not.
Nope, it's still parallel, right? If I put an axis right there, it'd still be parallel.
Yeah.
Right? What's the distance I need?
Wait, half S?
That's 1/2 S. That's 1/2 S.
Pythagorean theorem. Or
Yeah. Let me ask you this, Jesse. What's the whole distance all the way across? What's the main diagonal of a 45, 45, 90?
2s squared?
Root 2s. Do you remember this from class somewhere? Think about it there. It's s squared plus s squared square root,
Yeah, I forgot the square root.
which is square root of 2s squared. The s pops out. So it's root 2s. And then we have half of that. So what's our special distance here? Let me get a different color. What's this distance then? If the whole diagonal is root 2s, this is?
Root 2s over 2.
Yep. 0.7071. So that is what you plug in here. Got it? That's the plate. What's the moment of inertia of the bullet?
M
Mass of the bullet, which I think was M1.
root 2s.
That's not quite right. What do we need to do with that?
Square it.
Square it, because it's a point mass, right? It's so far from the pivot point. This is tough, isn't it? All right. All right. This shows you all of the stuff you need to know to do any problem. That's why this is a useful problem. It's not fun to torture you. It's fun to help you get better. And that's what I'm trying to do. That doesn't mean I'm successful or doing a good job at it, but that's what I'm trying to do. All right. Woo. Now let's look at the solution. Sorry about that. Okay. We got the lever arm. Here's the moment of inertia of the plate. Here's all this stuff drawn out. Here's all this, blah, 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 blah. That gives us a nice simple relationship between omega and V. Got it. So it turns out it does simplify quite a bit eventually. Notice I checked the units. Next, between stage 2 and stage 3, this is where it gets nasty. I did the bullet and the block separate. So Denna, I think, was talking about doing the heights of the bullet and the block separately. I showed you that here, or you could figure out the center of mass like this, and I did it that way. So I showed you both options there. You could either get the center of mass and get the center of mass height, or you could do each block separately and get the heights. Either way, you get this crazy result here that relates omega here. I could square this, set it equal to the previous. Oh my goodness. This was from, I think, our earlier equation, right? So you do that, you get this. Look at this. Everything is known except for M1, but this is pretty ugly. It's a quadratic formula. Do you see that? You cross multiply. Ugh. 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 There you go. Now, to be honest, normally you would give numbers for this problem, but I just wanted to show you that you don't need them. All right. That was intense. What do you think? Am I killing you? Medium? All right. That's a hard one. That's the hardest one probably in the entire semester right there. All right. Whew, got that done. All right. Now, here's what I would like you to try and do. See if you could redo that problem without looking at the solution later to see if you can remember all the different tricks that we had to pull. And then, right, if you could redo that one later, I think you'll be like, okay, I could actually handle these. And yeah, so that's something else I told the earlier class that might be worth trying. I imagined, what if you made a little flow chart for these problems where you said, look, if I have an angular, like what tells me it's an angular momentum problem, and then what I have to do. Yeah. Yeah. So anyways, yeah, I don't know if that helps you or not. All right. Should we take a short 5-minute break here after that pleasant experience? All right, everybody, take a quick break, and then we'll come back and we'll try one more. And I've got some positive things I think that you will experience in that next one. Fingers crossed. Yeah. So take 8 minutes. Screw it. All right. All righty. Hopefully that was the right time. I have no idea anymore. I'm in a land of space and time. All right. So hopefully that was a restful break. Let's take a look at another question here. All right. You know what? This 11.12 is really fun in person. It's just not fun online. That's the one where you have the wheel and you hold it and you spin it, and it's really cool, but it's all about feeling things, and you can't really feel something over Zoom. Same thing with this magic wheel. So let's skip forwards a little bit and let me try another one. Oh man, secret suitcase is another really fun one. This is one of my favorites in class. We sent Linda to the hospital a few years back with this demo. This is a 45-pound flywheel hidden inside a suitcase. This is kind of interesting, so let's talk about it. This, I don't know. This is basically a giant flywheel of some kind. It's basically a giant weight. Like, think of this like a plate from the gym. If you've ever lifted weights in the gym, a 45-pound plate, it's just a 45-pound weight essentially. And so what you're going to do is you get this thing up to high speed with a Dremel so that it's rotating and violently shaking, and then you close it and lock it. And then what you do is you have a student come up to the front of the class and say, walk in a straight line with the suitcase. And it's heavy, but they can do it. And you get like then you say, now turn right or left. And what happens is it's almost impossible for the student to turn because their arm almost gets ripped out of their arm socket. So let's try and understand why. Because this one you may not have seen as much. Let's say this is rotating with an extremely high rate. Well, that means L, which equals I omega, for this situation would be huge. I is big. This is a 45-pound weight. This is massive moment of inertia, right? A 45-pound disc is going to have a large I. And if you very slowly get it up to speed using a Dremel, this thing is rotating quickly. So I is big, omega is big, L is big. The moment of, the angular momentum is much larger than 0. Now, if you try to walk in a straight line, are you trying to change the angular momentum? When you walk in a straight line, does that change the angular momentum? What do you think?
No, I don't think it does.
No, that changes its translational momentum. And so you could do that. What about if you try to turn? If you try to turn, are you trying to change the angular momentum?
Yeah.
Yes, you're trying to change the direction of it. You're trying to change the vector. You're changing the axis. What is required to change angular momentum? A force, a torque, or work?
A torque?
Torque. If you have a large angular momentum and you want to change it, you need a large torque. Now, you are probably pretty familiar with this principle if I draw another diagram here. This is not a very good picture. What am I trying to draw here?
Bicycle?
A bicycle. Think about this. Isn't the bicycle very similar to this experiment? Most of the weight in a bicycle, well, not most of it, but a lot of it comes from the wheels, which are thin rings. If you ignore the spokes, right? The tire and all that stuff, you get 2 thin rings spinning. It's very hard to change its rotation state, meaning it's very easy to tip over a bicycle when the wheels aren't spinning. It's very hard, or much harder, to tip over the bicycles when you're riding it. This is why when you come to a stop on a bicycle, you might fall over. Whereas when it's running, it's actually a lot easier to keep your balance once the bicycle is moving. Once you're moving, you have a large angular momentum. It takes a large torque, or it takes a small torque a large amount of time. Either way, you want to think about it. You either need a large torque, or you need a time that torque can act that is large if you're going to change it. And so what happens is, on a bicycle, it's actually the time factor, right? You have more time to react before your bicycle falls over. And that's the issue. All right. So that's kind of interesting. Let's go back to here. So, well, whoops. I guess we just did that one. All right. Now, I know we've only got a few minutes left here. I want you to take a look at this 11.16. And I want you to give it a shot without looking at the solutions. I want you to think about it, and I'm going to give you a few minutes. I'm going to give you 4 minutes, okay? Take a second, read it, think about it. See if you could guess how to approach it. You don't have to do all the work, but see if you could get it to a point where you could do the work. I'm going to mute myself. You are welcome to talk amongst yourselves. I promise I won't bother you. Do you want breakout rooms for this or nah?
Nah.
Okay. All right. Let's try to talk about this a little bit. So, when you look at this problem, whoa, do you have any idea how you might start? It's okay to not know how to finish, but how might you start?
Well, to me, from the picture, kind of looks like a ballerina opening up. So I kind of think of a rotating object changes shape.
So what would you write down on the paper then?
I initial, omega initial equals I final, W final, because we know the omega initial
Mhm.
already. And then we can easily find the I initial.
Okay, so you're saying we know that. Can we find the I final?
Yes.
Do we know omega initial? So can we very easily get this part?
Yes.
Sweet. How would you plot this in part B? What would you do to plot it?
Excel.
Excel, right? Don't overthink it. How about part C? Any ideas how we might approach part C?
I got stuck there.
Okay, anybody want to try and throw out an idea on what you might do? We're trying to figure out the maximum rotational energy of the person moving outwards. What do you think?
So we're using the energy equation.
Okay, give me what's the energy equation you would use?
The one from earlier, the half I r squared, was it?
Half I. Think of what's the equation for regular translational kinetic energy? Do you remember?
It's half mv squared.
So then what's the rotational equivalent? 1/2 I is like M. What's the rotational equivalent of V?
Omega.
1/2
Omega,
I.
yeah. Yeah, good. Okay, once we get this, it says determine the maximum value of that. What are some different ways to figure out that maximum value? Oh, let me ask you, do we know what I is?
Yes.
Do we know what omega is?
Yeah.
Yeah, right there, right? So how could I figure out its maximum value? How could I figure out its maximum value?
Would it be a derivative?
You could take a derivative. The other way you could figure out is plot it and look for the top of the plot, right? If you take the derivative, what would you take the derivative with respect to? So I'm going to call this the rotational kinetic energy. I'm just going to call it R for right now. Oh, that's a bad idea. How about I call it K? Let me undo that. Let's say the rotational kinetic energy is the letter K. What you said, take the derivative of it. So I'm going to say with respect to what? dk d what?
R.
Little r. And then what do I do with that? Take the derivative. You're trying to find a maximum. What do you do when you take the derivative? When you're trying to find a maximum?
Equal to 0.
Equal to 0. Then solve for what? In
Would it
this
be
case, I would solve for R, and that would be called R critical. And then I take that R critical and plug it back in. All right. Do you feel like you can understand this problem? Maybe we didn't do it all, but do you feel like you can get this? I took this problem from an MIT test. You can do it. It's not easy, but you can do the same stuff that people do at MIT, at Harvard, at Berkeley, at anywhere. Now, when we started this class, maybe not, but at this point, your tools are built up enough that you can learn anything you need to. So I like to bring this up and point out you are just as good as people from these bigger schools. You have an edge on them because I actually care about you. You have a disadvantage in that I'm tough, but I want you to be able to compete with anybody in the world. And that is why I'm tough on you. That is the takeaway, is you can do it. Let's look at the solution just for fun, right? The extra parts are not on the MIT test. So this going here, that's just me. All right. So that's me having fun. And by the way, this is a typo. I have done it. All right. Part F, I have done it. So when you look at this one, there it is. There's omega. And here's that derivative. Here's what the energy looks like for the person. There's some maximum there. And so you know how to do this stuff. You could do second derivatives, blah, blah, blah. This relates to electric circuits. There's a bunch of comments. Here's what it looks like. Just to point out, you may be saying that person is not a point mass. Well, you're right. I plugged in some realistic values, and look at this. The maximum is at about, 0.7, I think. The maximum is at about 0.7, regardless of whether you treat the zombie as a point mass or not. Do you see that? Go ahead, Gonzalo.
So what would I do if I wanted to find the minimum?
Well, there is no minimum. And I mentioned that in the solution here. Or the minimum would be at the initial state, right? Because the trade-off here is when the person's on axis, they have no rotational mass. They have mass, but no rotational mass. As they move outwards, they have less and less speed. So there's some trade-off. Now, I want to remind you of something before I call class, just where this is in the workbook, just in case. One of the things that students struggle with is, when do I use what? That's what page 93 through the end of the book is for. If you're sitting there going, man, I'm just not good at knowing when to use these, look at this one. Which conservation laws apply? Which conservation laws apply? Which conservation laws apply? If you do like part A of all these, you'll be much better at that and identifying, because you're probably pretty good at math once you know which equation to use. So that's what those problems are for. Since we have Phil here, Phil, guest speaker. Anything you want to recommend to them about angular momentum, or any takeaways you have for angular momentum? And if you guys need to take off for your next class, that's fine.
For that stuff?
Yeah. Anything you remember about chapter 11? Like 11 point nasty, the block hits the bullet hits the block and it.
Oh my God. I don't know if I remember enough to give good advice, honestly. Not
All
this
right.
chapter.
All right, that's cool. All right, so they just had a quiz today, Phil. So I'm probably going to be answering some quiz questions for you may want to.
It's all good. I don't have any burning questions, so I'm
okay,
not worried about
so it'll probably be at least 10, maybe actually probably about a half hour.
I'm not worried about it.
Just letting you know. All right, feel free to get out of here, people. And if you want, we can go over the quiz now. And any quiz questions? It's only 20 points, but we might as well talk about it. Hopefully the quiz made sense.
It did. I just made stupid mistakes.
I
got
just
you.
keep like, I keep getting stuck. Like, okay, which, like, not knowing which formula to use. Like I know I understand the concept. I just like, and I can do the math. I just get confused. Like, okay, do I use this one or this one? If that makes sense.
Yeah, no, I totally get it. There's studies that have been shown that students, when they take physics, when they come in, they feel like they have a certain grasp of it. And then when they leave, they feel like it's worse, because you realize how much you don't know. And you're like, that what a lot of students feel like is it's all about which formula do I grab? And up till now, a lot of it has been exactly like that. So today, I don't know if you noticed, I was trying to show you the key is to understand when you grab a formula, because once you do that, it's easy. And that is That's it in a nutshell, Gonzalo. It's hard to tell which equation to grab. The key is understand the concepts which give rise to grabbing an equation. I think that does that make sense, Gonzalo?
Yeah, it does. And I still need to work on that because like I've
Yeah.
done some of the workbook problems, but the only one I recognized was the pulley one. I had trouble with the rod one.
Oh, shoot. That was like parallel axis theorem, I think.
Yeah, I was thinking it was a calculus one for some reason.
Yeah. So you could do it with calculus. I hadn't thought of that, but you could do it that way and plug it into Wolfram Alpha, and that should also work. Yeah, that would be another acceptable way to do it if that's how you saw it. And with Wolfram Alpha at your side, it might be doable. But, another thing that you could do is you could cut that rod into two pieces and say there's this chunk and that chunk with two masses and say I'll add this rod to that rod. That's another way you could do it. But the easiest way is just use the parallel axis theorem. Yeah, so if you look on page, let me remind you, hold on. Top of page 64 is kind of my checklist for the order in which I approach moment of inertia problems. If you have a problem with a nasty moment of inertia you need to figure out, I go through that checklist on the top of page 64. First, can I just know the answer from the table and add them up? If it's not matching the table, can I use the parallel axis theorem? And then if that fails, then I go to calculus. So that's the checklist that I was hoping you were going through in your brain or literally. Does that go ahead?
That didn't ring a bell, but now I know to use that. So that's going to be helpful.
Yeah, there's so much we say in a one class period. I know I said that during the class, but that doesn't mean you remembered it because your brain could have been full that day, right? You only can remember about 7 things, 2-hour lecture. I think we do more than 7. Oh yeah, 5, yeah. 7, you're elite, right? 10, you'd be like world class. All right. Other questions?
Okay, so number 1, I didn't get full points for it, but
Do you want to
so
screen
I know
share? Because I don't know
yeah,
which questions you had.
Yeah, I'll do that right now. 1 second.
Yep. Take your time. Go ahead, Alonzo, while he's opening that up.
All right, I was just gonna ask for the second problem. It was the parallel theorem, right? For the moment of inertia.
What did you have? Did you have like a disc or a rod or something?
I had a rod.
Yeah. So, and then did I give you some masses and distances, and it was just basically parallel axis, right?
Yeah, but you gave us the problem was the distance from the end of the rod to the.
Yeah. So then, what do you have to do?
I had to do the dl/2 minus that, and then use that as the distance.
Yes. So you have to subtract it off and then use the distance from the center of mass, because it's always the distance from the center of mass you have to use. Got it?
Yeah.
Which would be the middle of the rod.
Mm-hmm.
Okay, we could look at that in a minute. All right, so
add it to leave. I just wanted to make sure.
Yeah, something like that. And you could redo it later. And if for some reason there's a mistake, just let me know. When you make 8 versions of this, it's quite possible I missed a squared on one version, but not on another or something like that, right?
Mm-hmm.
I don't think I did, but we could check it. If you really believe it, we'll check it, all right?
Yeah, no, I'm pretty sure I messed up somewhere.
Okay, yeah, but go ahead and redo it. And if you're confident, then we'll look at it. Okay, so looking at Gonzalo's screen here, which force causes the smallest torque? Which one did you think?
I put 3 because like it's the one that's closest going to the pivot.
Yeah, the smallest lever arm. Okay. And then what was the next one? Which force causes the largest torque?
Yeah.
Which one do you think it is?
Now that I think about it, I think I messed up and it should have just been 1 alone.
Yes. Because they don't have the same lever arm. Hold on. I don't know if I can't annotate, but do you agree the lever arm for 1 is the full side S?
Yeah.
What's the lever arm for 2?
It's like, I think it's like parallel to it.
It's S over 2 because it's only half the distance. I can't draw on yours here. If I do this, right?
Yeah, let me go back to Zoom.
Oh, sorry.
Okay, I'm back.
So, right, the idea was the pivot point was right in the middle. So this lever arm was S over 2 to this force. Let me use a different color.
Yeah, I'm starting to see my mistake. For some reason, I thought that both would cause like torque.
That's the line of action for that one.
Yeah.
Whereas the line of action for this one was the full distance up to here. That's a full S. And so that was what I was trying to work in this problem, was basically look at lever arms over and over and over.
Yeah, I see my mistake now for that one.
And it turns out to get a physical intuition about problems, that lever arm is crucial. Because you could just be like, well, it's about the same size force. The lever arm's bigger or smaller. Oh, this should be the dominant term. Why is it so big? It helps you check your work so much. That's why I'm focusing on that. Okay, good. You won't screw that up on the final when it matters. That's what matters. Okay. All right. What else?
Can I show my mine real fast? Because I think
Yeah.
I know what I did wrong, but I just need to make sure.
Yep. Okay. Are you talking about question 2? Oh, we're still live streaming here. I didn't realize that. Is that okay?
I think that's good because I know a lot of my other classmates had questions, but they went to math.
Right.
Yeah, I don't care.
Okay. Yeah, but I don't want like somebody to see your score accidentally, and I apologize. I didn't mean to do that.
Oh, I don't care. Like, shoot.
Okay. Yeah. Sorry
I
about
have
that.
a strong feeling we all have pretty much around the same scores.
Yeah. We'll look at that later. But so what did you do on this one?
Okay, really, I did the parallel axis theorem, but I think I made a mistake by using the wrong inertia for the disk. Was it supposed to? I used the 1/4 mr squared. I'm pretty sure it's supposed to be.
It should be 1/2.
Yeah, I kind of figured.
And the distance you would use is d equals z over 2 minus y.
Yep.
Yeah, and so then we know it's either 1/4 or 1/2 mr squared.
I have the same thing.
Which in this case is, what is the radius? Is it z over 2?
It's 0.995 over 2, but yeah.
Yeah,
But
z over 2.
Too, yeah.
Yeah, gotcha. All right. So and then in this case, the 1/4, if we have a disk like this, yep, this is the 1/4, but that doesn't look like yours.
Yeah, I realized it the last 5 minutes when I was doing it. So
yeah, and well, this is actually a good reason to do this as a quiz when it's only worth 20 versus the final exam when it's worth 20% or whatever.
Exactly. I learned a lot more about getting stuff wrong than I do about getting it right. So
yeah. So this is a tough one, and I think you get another go at it next week when it's basically chapter 11 and 10 are kind of mixed together, right? The moment of inertia always comes up.
Yeah, and then I've been sick the past 2 days. So.
Yeah, and so just to be clear, I just want to make sure you did I parallel equals I center mass.
Correct. Plus
mass times distance squared. Okay.
Oh, that's the formula I should have used for the rod.
Exactly. And that's why
Okay.
this gives you an idea of how I mix things up. I give one group a rod, I give one group a disc, but the math is essentially the same. The problem with the rod that people have is people oftentimes use the moment of inertia at the end, which is 1/3 ml squared, but you can't shift using that formula. You have to shift from the center. And so that's a different, right?
Now I know what I should have done. That's okay.
Yeah. When you have the rod problem, you have to use 1/12 ml squared. And then you're like, oh crap, L. Okay, so it's a little bit different with the rod than the disc, but there's a
I-
different error people make in that one.
I don't think I'm gonna make the error again because like I didn't know how to shift it, but now I know
Yeah.
you're gonna you're gonna use a center mass equation and then you're gonna add the difference.
Yep.
Okay.
Okay, Jesse, was that your last question, or do you want to look at the next one?
Might as well go.
Okay, so which one? Question 3 or question 4? Let's read question 3.
Sorry, computer issues. Yeah, 3.
Okay. So if they're the same size, which way is this thing going to rotate?
I was thinking it was going to go counterclockwise.
Yep. And then is it going to rotate at a constant rate?
Well, if it's releasing from rest, probably not.
Alpha is greater than, yeah, it's basically, so it's rotation with increasing rate.
Yeah.
So this should have been increasing rate. It's going to rotate and increase in speed.
Yeah, I realized that afterwards. And then for the bottom one,
Okay.
it's not them not moving at the.
Yeah, this one's going to move twice as fast as that one.
Yep.
Right? Because they have the same omega at any point in time. And since V1 equals big R times omega, whereas V2 is small r times omega. Got it?
Yeah, I realized that at like the last second too.
Okay, then the next one.
Same.
So it's not constant rotation rate, it's constant rotational acceleration. That's what's constant. And then in this one, it's do sum of forces for this block, sum of forces for that block, sum of torques for this one, right?
Okay. Okay.
And-
yeah,
and
I
so-
didn't try this one yet.
I remember you went over it in lecture once, like you had like this whole like plot thing for like the sum of forces like T1 and then like T2,
Yeah.
but I just couldn't like remember how to set it up.
It's almost exactly like it's not exactly the same. Actually, it's nearly identical to 10.56. The only thing different is the moment of inertia. So if you want 10.56, we'll show you exactly how to do that one. Okay?
Sweet, I circled it.
Yeah. If you look at it, you're like, oh man, it is the same. All right. And then I said magnitude, so that just means absolute value at the end.
Is that
Cool.
the Atwood problem thing? Like, or
It's also very similar to the Atwood's problem, but there's 2 different radii. So it's nearly identical to problem 10.52 as well.
okay, yeah, I'm gonna.
Except there's different radii, and that's what's different in 10.56.
What's another problem that's similar to the rod one that relies on parallel axis theorem that I could work out?
That would be $10.16.
Perfect, thank you.
Yep. And if you're wondering for the disk, we talked about this in 10.20. Why the disk, like that was when we talked about which number from the table you have to get out of it. So if you had the disk, it was 10.20. Both of those are on page 62. All right. Is that good?
I'm good. I'll stop sharing.
Should I stop the